Welcome back. I am Anshu and you are watching Bottleneck. This is the Agenti CookBook series where we learn and implement design patterns for AI applications using hands-on examples. In our previous video, we learned how AI agents can go beyond their training knowledge by using external tools to perform calculations and execute business-specific tasks. This is called tool use pattern and it's a key building block for creating smarter, more capable AI agents. If you missed on my previous video, I will be sharing link in the description below. Alright, in this video, we will start implementing tool augmented arithmetic agent. Along the way, we will explore several powerful agentic AI patterns including react, reason, act, observe, agentic loop, stateful memory, and the reducer pattern. Together, these patterns help agents reason effectively, maintain conversational context, learn from intermediate outcomes, and deliver more intelligent and trustworthy results. What is tool augmented arithmetic agent? Large language models are great at understanding and generating language, but they cannot inherently access custom business logic or specialized enterprise functions. A tool augmented agent bridges this gap by allowing LLM to intelligently invoke external tools when needed. In this implementation, we will build a simple arithmetic agent with custom tools for addition, subtraction, multiplication, and division to demonstrate how the tool use pattern enables an AI agent to combine reasoning with a reliable tool execution. All right, let's walk through the agent workflow. The process begins by initializing the LLM and the arithmetic tool using the tool use pattern. When the user submits a query, it is maintained through a stateful memory pattern. The LLM then analyzes the request in the think phase of the react pattern and decides whether a tool is needed. If required, the workflow enters an agentic loop, invokes the appropriate tool, and returns the result. Through the reducer pattern, each tool result is added to the conversation history, preserving the context. The LLM observes the result, reasons again, and repeats the cycle until the task is complete. Finally, it generates clear answer and waits for next user request. Alright, let's start the implementation. Let's create the methods that are required for the tool. So let's create the multiply. Okay, with it will take two values, a int, b int. Okay, and it will return an int. We will keep it simple for the sake of our demo. Now normally what we know that in multiply we have a two input parameters, so the formula goes as a star b equals to ab. This is the standard formula for multiply, but here we will add a twist. We will tweak the logic here for the multiply to customize it based on our requirement. The objective is to see whether the same multiply method that we are implementing here is being used as part of the tool. So if we multiply something with 0 in the current structure, so 0 into 1, 0 star 1 would be 0, but what we will do is we will replace any zeros by 1 so that it will never turn to 0, and we will see whether this change is reflected in our tool use pattern. Okay, so let's update the header accordingly, because the LLM is going to read your header to understand what exactly this method is going to do and how to apply them. All right, so let's write multiply a and b, but if either of them either is 0, add 1 to it first and then proceed for multiplication so that the result is never 0. Okay, so now this is our intent. All right, so how it is going to be, let's provide the args. Let's make it very clear for LLM. Okay, that this is the first int, and b is the second int. All right, let's give it an indentation. Okay, now let's implement the method. So if a equals to 0, then it should be a plus 1. Okay, all right, else we will have, if b equals to 0, then again b plus 1. Okay, and finally return a star b. A star b. This way we have made sure that whenever we pass a value, it will never turn out to be 0. The multiplication cannot turn anything to 0. So this is our custom multiplication method. But this is just a method. It is not yet a tool. So how can we make it a tool? We will import an annotation from the LangChain, that is tool. So let's import it from LangChain dot tool, import tool. Now, all right. Now we have the tools in our scope. We add an annotation here as tool, and this makes it as a tool. So what difference does it make? Well, the tool definition, each function is decorated with tool first of all. Then it automatically generates couple of things, like it will generate a schema which is basically JSON based schema, and it will be name, description, and the parameter type. So whatever we have provided here will become part of the schema for this tool. All right, so first of all, using tool, it keeps the Python function as a normal Python function which we can test. Secondly, it generates a JSON schema that we have seen, and the LLM understands based on that schema or based on the description what this particular tool is supposed to do. So this way we induce the tool use pattern. Now let's create the other tools that we have. So we have add, we have subtract, and we have divide. So let's create add. So dev add int comma b int. Okay, and it is going to return an int. All right, now similarly, okay, it will be small I. All right, so now similarly we have to give an header here. So what it does, it is basically a simple add. So adds a and b. All right, and let's give the arg will be same as before. We have two arguments, a and b. Okay, it is best to give all possible information to the LLM as part of the header, so that LLM can make a decision on what to do and how to use it. So it will return a plus b. Okay, similarly we will do a subtraction. Let's copy this method, and so it is subtract a and b returns. So it will be subtract. All right, so a and b returns the int. Again, everything is int, so it returns a minus b. All right, or we can say in case of subtraction it should be b minus a. Okay, it should always use the right hand side or the next value to subtract the first one. However, you can customize it as you like it, and you can see the difference in the result. All right, now finally we have divide. So let's copy it again, divide. Again, divide is going to be same. We will keep it simple, divide. So this divide is same as It goes for add or subtract. We have a and b. So first value is a, second value is b. Let's keep it simple, return a and b. Now let's make them tools. Add the tool annotation. Okay, once we add the tool annotation, everything becomes a tool here. So this induces the tool use pattern. All right, let's update the name of this tool. Okay, now we have the tools created. We have initialized the tool use pattern, but these tools are not yet visible to our LLM. So we need to first bind this with our LLM. For that, we need to create an array of tools. Okay, so we call it tools, and we will add in here add comma multiply. Then we have divide, and finally we have subtract. Okay, so this is basically a Python list which has 4 tool as the functions. Now we need to create tool by name dictionary. So this dictionary will be used by LLM as a reference, which will have a key as the name of the tool with respect to the function body as the value, and accordingly the LLM will take a decision which tool to trigger. All right, so let's create tools by name. Okay, you can think of it as a table, a lookup table, which is used by LLM. So we can have now tool dot name. Okay, is to tool for tool in tools. All right, so this way we have created a lookup table. Now we need to bind them with LLM. So for that we need an LLM. Let's import our LLM. Import LLM utils. LLM utils as my LLM. All right, let's initialize the LLM here. LLM is equals to my LLM dot. Okay, I need the grok LLM. Now watch closely. Let's bind the tools with LLM. LLM with tools. Okay, so we will have LLM dot bind tools, and we provide the tools. Now what benefit does it provide? Once we bind the LLM with tools, other than a plain text output that we had seen in our previous implementation, an LLM can also return a structured tool call. Now this tool call will be used by an LLM to understand whether it requires to call another tool and evaluate and provide the answer, or it's end of the query that user has provided. And that brings us to the end of our part 1 for our tool augmented arithmetic agent implementation. In this video, we have laid the foundation by understanding the core concept of the tool use pattern, the architecture of the entire implementation, and the design patterns that we are going to see. Now, in the next part, we will bring everything together by building a complete land graph workflow. We will create and connect the required nodes, implement agents decision making logic, and see the key design patterns such as React, agent loop, stateful memory, and the reducer pattern, all working together in a real world application. We will then run the solution end to end and watch the tool augmented agent come to life, demonstrating how an LLM can seamlessly collaborate with the external tools to deliver accurate and reliable results. If you found this video helpful, please take a moment to like, share, and subscribe for more practical insights into AI architecture, agentic systems, and modern design patterns. Thank you for watching, and I will see you in the next video.